All right, welcome to this masterclass explainer for Beyond Design Codes. Let's jump right in, because today we are completely stepping outside the standard rulebooks and diving into a world where structural engineering is pushed to its absolute limits. We are talking about engineering for the unthinkable.
So I want you to ask yourself a question. How do you design a building for an event that just flat out defies the laws of normal engineering? I mean, really think about that for a second. We are dealing with massive stakes here, and the sheer destructive power of extreme events. It requires an entirely different philosophy than, just building for everyday wind loads or gravity.
Here is our game plan for today. We're going to cover the anatomy of extreme events, high strain rates and inertia, the physics of blast waves and impact, performance-based engineering, and finally, simulating the unthinkable.
Okay, let's get into Section 1, Anatomy of Extreme Events.
So, what exactly makes an event extreme to an engineer? Basically, extreme events are high-energy occurrences that have two very distinct signatures, a massive loading magnitude and an incredibly short time duration. We're talking about man-made events like a missile impact or a massive industrial disaster like the Beirut port explosion. Now, these events obviously have a very low probability of actually happening, but when they do, they carry extremely high cascading economic and structural consequences.
So, your standard building codes? Yeah, you can pretty much throw those right out the window here. Normal design usually focuses on serviceability, right? Making sure a building doesn't sway too much or trying to prevent minor cracks. Extreme event design completely abandons that. It prepares for severe damage. The goal isn't keeping the building in pristine condition. It's strictly about collapse prevention and ultimately keeping people alive.
Which brings us to Section 2, High Strain Rates and Inertia.
When an extreme event hits, it applies this impulsive load way faster than a building can naturally respond to it. And this triggers something called the dynamic increase factor. Basically, a sudden pulse wave travels through the material in just mere milliseconds. It causes local damage that actually propagates through the structure before the rest of the building even knows it's been hit. It's wild. It literally alters the material's structural DNA in real time.
And here is a truly counterintuitive paradox for you. Because the loading is so unbelievably fast, the material actually stiffens. So the sheer strength of everyday concrete and steel drastically increases. But there's a really dangerous trade-off here. As that strength goes up, ductility, the ability to bend and absorb energy, plummets. The materials become dangerously brittle, and this forces engineers to completely rethink exactly what they are building with.
All right, Section 3, the physics of blast waves and impact.
Think of a blast wave, kind of like a popping balloon, but on a massive, destructive scale. It follows what we call a Friedlander profile. In a fraction of a millisecond, boom, a supersonic shock wave hits. This is immediately followed by the positive phase, creating a massive overpressure. And then, the surrounding air creeps back in to fill the void. This creates a highly dangerous negative phase. It's essentially a vacuum suction that pulls outward on the structure, which is then followed finally by the thermal effects.
Now, impact events, like a vehicle crash or a direct missile strike, have their own specific kinetic anatomy. It starts with the freefall approach. Then comes the loading phase. That's the actual violent hit where the rapid deformation happens. After that is the unloading phase, where the structure begins to reverse. And finally, fly off. For the structural engineer, the entire battle is won or lost in that crucial loading phase. The absolute main goal there is maximizing energy absorption.
Okay, get ready for a number that's probably going to shock you. 8 to 10. Because of confinement and the reflection of a blast wave against rigid surfaces like concrete walls or the ground, the reflected pressure hitting a building can actually be 8 to 10 times higher than the initial free field overpressure. It's a massive multiplier effect.
So how do we possibly calculate and defend against this kind of force? Well, we use the scaling law. This law proves that blast pressure is driven by two main things: the explosive mass, which we measure as a TNT equivalent, and the standoff distance. Just like stepping away from a roaring campfire, increasing the standoff distance from a threat exponentially reduces that blast intensity. Honestly, it is the most powerful architectural defense mechanism we have.
Moving on to Section 4, Performance-based engineering.
So, knowing all these catastrophic physics, how do we actively design for them? Well, conventional design generally uses a one-size-fits-all limit for serviceability. But performance-based engineering, or PBE, is a much more tactical framework. This is where engineers essentially accept the hard truth that some damage literally must happen. Instead of trying to prevent every little scratch, PBE categorizes acceptable damage levels based strictly on a structure's usage and its importance. We are optimizing for the survival of the most critical elements.
Engineers categorize these tactical sacrifices into different performance levels. For a critical facility, let's say a hospital, we demand immediate occupancy. That means only minimal damage is allowed. For your standard office buildings, we might aim for life safety, meaning we allow significant damage just as long as everyone inside can evacuate safely. And at the absolute extreme end, collapse prevention. The structure is severely damaged, essentially sacrificed, but it does not fall down. We achieve this using highly ductile materials or sacrificial claddings that are literally designed to die so the occupants can live.
And the thing is, we often have to design for multi-hazards simultaneously. The design priorities here are intense. We have to prevent single-point failures, ensure redundant load paths so the extreme energy always has somewhere else to go, and we absolutely have to protect non-structural components like medical gear and data servers. And we have to balance conflicting hazard responses while doing it. Because honestly, it really doesn't matter if your hospital's concrete frame survives the blast if all the internal HVAC systems immediately explode.
And finally, Section 5, Simulating the Unthinkable.
Obviously, to validate these incredibly high-stakes, multi-hazard designs, we can't just go out and blow up buildings. So we rely heavily on finite element simulation. Software tools like LS-DYNA or ANSYS provide us with virtual mathematical testing. They act as explicit multi-physics solvers that map out those high strain rates, nonlinear material behavior, and complex failure mechanisms. This software allows us to simulate the unthinkable without conducting deadly and, let's be real, astronomically costly real-world explosions.
But hey, let's be real for a second. There is a hidden reality here. Simulation software strictly follows the golden rule of garbage in, garbage out. Despite all these advanced algorithms, there is a super intense computational cost when you're balancing mesh sensitivity. Contact algorithms can suffer from nasty penetration errors, and modeling complex concrete failure, that requires a continuous need for physical material calibration. Basically, we constantly have to run physical experiments just to validate what the computer is telling us.
Ultimately, all of this boils down to one incredibly heavy burden for the structural engineer. We constantly have to establish a cost versus protection trade-off. We are forced into balancing highly constrained, real-world budgets against the strict mathematical limits of human safety, all to try and achieve a perfectly balanced performance objective.
So I want to leave you with this final thought to take away from this masterclass explainer. When a structure is asked to survive the completely unimaginable, how much tactical sacrifice is truly acceptable to build a resilient infrastructure of tomorrow? Think on that. And hey, thanks for joining me on this deep